approach is, from based on that you can see. So in knowledge-based approach, I can say that it rely on a knowledge resources like wordnet, results. Many use grammar rules for disambiguation. May use the grammar rules for disambiguation. They use the hand-coded rules for disambiguation. Or you can say that in a machine rule-based approach, you can say that rely on a corpus. Train a model using a tag or untagged corpus, probabilistic or statistical model. See, how you can say that okay, whether the particular means dog as an animal is more probable than this. Means how it is decided if this one is more probable than the second one. So for that, the different approaches are used, and one of the approach that is probabilistic and statistical model. So that thing that we will discuss in the next lecture, that is the statistical natural level processing. So see, right, I will not explain you how you can say this one is more probable than the second one. But see, this thing that we will discuss in the statistical natural language processing, that I will explain you how you can say the one sentence is more probable than the other. Okay, so based on that, see, these are the different approaches. Based on that, it is decided, and always in a lexical, what happens? See here, the two meanings are there. One is a dog as an animal, and one is a dog as a detestable person. So what happened here? You can say that select the meaning for context. So here you can say that every time the word has only one sense, right? Whenever every time the word has only one sense, and whenever it appears in a document, so identify that exact sense, right? And how you can decide? So based on this probability, you can define that exact sense, right? And when you find, so that means I can say that the dog is the more probable, but for that you have to that we have to do that. Okay, so every time there are so many meanings for that. What has a multiple meaning, right? But when it appears in a document, but you have to identify according to the context, particular context, you have to identify that exact sense, everyone. Okay, then after we have discussed to disambiguate the word, we need a word relationship. Now this question, this thing I will explain, that is the chair emphasis the need for adult education. Okay, so here in this case, see the statement, the chair emphasizes the need for an adult education. So now here, the word which is disambiguate here, that is what chair. The word which I want to disambiguate means the process of identifying which meaning of the word is used in a context. So here in this case, the chair is a disambiguity here. So here I can say that chair means a piece of chair, or I can say that a person holding a chair. So chair can be either a piece of chair or person holding a chair. So now when you so here this particular word have a multiple meaning, right? Now, but when we look at this sentence, then what happened? What is the meaning of the chair from the context? So when you read the sentence, then it is clear that we need a person, need a person. So as the emphasis is about talking, so it helps us to identify that the piece cannot talk, and that's why in this way you can say that it is here in this case you can identify that we are talking about a person, we are not talking about the piece of furniture. So in this way you can identify the word sense disambiguation. Right now, then after the another example that we have discussed, everyone. Sorry. Now, then after another thing that we have discussed, that is one of the satellite channel that I have seen on the TV, that look at the sentence, watch what you want when you want. Now listen in here, the same way there are two senses of watch. Now the one is, the watch means to take care, be careful, and another watch is, just wait everyone. So the words have a multiple meaning, right? But we need to identify. So here that means you can read in that way. So one meaning of the sentence is be careful what you want when you want. So here you can say that the words are have a multiple meaning. We need to identify at a given context which meaning is suitable to use. This thing that you have to remember in a lexical everyone. Okay. Then after we have discussed syntactic analysis everyone. So here in the syntactic analysis, what happened? Though remember in a syntactic analysis, all of you know in a CC subject, in a syntactic analysis, it checks the grammar in a sentence and it arranges the word in a manner that represents the relationship among the words. So what the syntactic analysis will do? It checks the grammar in a sentence and arranges the word in a manner that represents the relationship among the words. So after in a previous phase, what happened after the word are processed? Now then after the structure detection is done. So here you can say that the problem of converting a sentence into a tree-like structure. This is called the problem of parsing. All of you know there are different parsing are there, top-down parsing, bottom-down parsing. These are the different parsings are there, right? Now listen, this NLP is a very wide topic, right? So I will not explain you each and every content in deep. So I will give you a brief overview so you have our idea about the NLP. It's a research subject, right? So just I will explain you the some of the basic concepts. Just I will give you a whole overview so you can understand how exactly the things are done everywhere. Now, there are some challenges. Means there is some means ambiguity in syntactic ambiguity. Now, my question is, see, before that, I will explain you in a syntactic analysis what happens. Suppose the question is, repeat. I say that car you have. Again, I repeat. My sentence is car you a have. Okay, now if this type of sentence is there, then what happens? This particular sentence has no correct meaning. So now, and also is not a grammatically correct. So now what happens? This sentence, it will be rejected by the syntactic analysis. Okay, now each and every phase have some ambiguity. So now when the syntactic ambiguity is occur. So listen, a syntactic ambiguity occur when a single sentence can have a two or more possible meanings. Again I repeat, a syntactical ambiguity occur when a single sentence have two or more possible meanings. So suppose I can say my statement is if you say to your friend, call me a cab, CAB. Again I repeat, if you say to your friend, call me a cab, CAB. So which generally means that you want to call a taxi for a going somewhere. But your friend will understand it as you are asking him to call you as a cab. Means see here you can say that for this particular sentence can have a two or more meaning. So then the syntactical ambiguity can occur, right? So now another example I want to tell you that is see the sentence parallelism. So here the scope of ambiguity means that old man and woman were taken to a safe location. Now see, when you read the statement, then for the woman, right, it's very easy to understand. Listen everyone. When you read that this type of sentence, then for the woman it's very understand, very easy to understand. But see, what about the computer? In a when the process of this natural language understanding is done. So what about the computer? So in a computer it's very difficult to understand because see here the scope of this word. That means here I can say that the old man and old woman. So here I can write old man and woman means I can write in this way old man and woman versus you can say that see here when I write this that means I can say old man and old woman versus I can say that only the man is old but the woman is young, right? So here in this type of sentence you can say that the question is who is old, are both the man and woman is old or only the man is old, right? So this type of question is arise right? When this type of sentence is there. So here the single sentence have a two or more possible meaning, right? Now similarly, all of you see the second sentence, that is no smoking area will allow hookahs inside. Now see here in this case, actually what happened, the meaning of no means it's a quantifier. The meaning of no, that is not any. So I can read in that way, not any smoking area will allow hookah inside, right? So here there are two meaning of this sentence. See, if I write the one meaning is, see, if I write the not any smoking areas which allow hookahs inside, means here the meaning you can say that you cannot find any smoking area which will allow hookahs inside. Okay, this is one meaning. Now the another meaning is there are some special areas like smoking area, they are allowed hookahs inside but not allowed cigarette. They are allowed hookahs inside but not allowed cigarette. Right? So this particular sentence have more than one meaning, then syntactic ambiguity can occur. Right? Now the another example that I will explain you so you can understand everything. Now the another that thing that we have see, that is the another ambiguity, that is propositional phrase attachment, means the possibility of the multiple phrase attachment. Now see, here I can say the sentence is, I saw the boy with a telescope. Now see, it's very easy for a human. But see, for a computer, it's very difficult task. See, when this type of sentence is there, then what the computer want, see, there are multiple ambiguity in this particular statement. See that. I saw the boy with a telescope. So here you can say with a telescope is attached to what? The boy also. So here the two meaning, one meaning I can say that I saw the boy. See, read this sentence, you can understand. I saw the boy and he had the telescope. And another is I saw the boy with the help of telescope. Right? So these are the two things that we have discussed in last lecture. So I think you can understand. Another is I saw the mountain with a telescope. So here I can say that, see, the question again arises, telescope between me or with a mountain. But see, normally you can say that the telescope is not with a mountain, right? So simply you can say that I saw a mountain using with a telescope, right? So but see, here there is no ambiguity, but there are some places like Arizona where the telescope are installed in a mountain, right? So that's why here the two meanings are there. So I saw there are two meaning is there. Okay, again there is an ambiguity here. And the last one, that is I saw the boy with ponytail. So here always you can say that the ponytail cannot be an instrument of saying. So the ponytail is with the boy only, and that's why in this particular sentence there is no ambiguity. Okay, so these are the different cases that we have discussed in a syntactic ambiguity. Now the next phase, that is semantic analysis. Now this particular part that is new for you. So in last lecture up to this that we have discussed. So for continuation, I have repeated again. Otherwise, you can't understand. So that's why the same thing I have repeated again in today's lecture, everywhere. The next is the semantic analysis. So in semantic analysis, it derives an absolute, means the dictionary definition, meaning from the context. The dictionary definition, meaning from the context. So it determines the possible meaning of a sentence in a context. In semantic, it determines the possible meaning of a sentence in a context. Okay, so here you can say that the structure created by syntactic analyzer are assign a meaning. Whatever the structure created by syntactic analyzer, that are assign a meaning. So the structure for which no such mapping is possible, that structures are what? Rejected. Now consider this sentence, everyone. I saw the boy with a ponytail. I saw the boy with a ponytail. So here you can say that here only one meaning is found, as the others are not possible. Why? Because I saw the boy. So see here in this particular sentence, you can say that The ponytail cannot be an instrument of saying it is only with the boy. So here only one meaning is found and the other are not possible. Okay. And then after that what happened? Even after the syntax and the meaning of the individual words have been reserved, there are two ways of reading a sentence. A dog is chasing the cat and the dog has been domesticated for 10 years. So here it represents the particular dog and here it specifies the dog. Right. So just in semantic what happened? So in semantic the structure created by the syntactic analyzer are assign a meaning and structure for no such meaning is possible. That type of that structures are rejected. So this thing is done in a what? Semantic analysis. I think all are clear to you. Now then after another is a pragmatics. Now see sorry. In a pragmatic means, it derives the knowledge from the external common sense information. Now see, all of you know in previous case, the sentence is read that sentence everyone. What we have discussed? Old man and woman were taken to a safe location. Old man and woman were taken to a safe location. Now consider that sentence everyone. Now see here in this case all of you know the old man and woman. So whether the man is old or woman is old, or the second case that we have discussed the man is only old, right? So here you can say that old man and woman means man is only old and the woman is young, as opposed to old man and woman, that means the man is old as well as the woman is also old, right? So here you can say that in this particular first case, in old man and woman were taken to a safe location since both the woman means young woman and old were likely to taken to a safe location, right? Here the young woman as well as the old woman were likely to taken to a safe location, and here you can say that the old men were also taken to a safe location. So here in our presumption would be that the word old qualifies the only a male. So imagine, listen, in this case here I can say that means the both means old man and young woman were taken to a safe location. Similarly, old man and old woman were taken to a safe location. So here the presumption would be the word old qualifies only for a man. So here imagine there is an attack on a region or a country and the man, when woman, everybody take to a safe location. So young man of course would go and fight the enemy, right? And the old man will have to be taken to a safe location. So here only the first reading that you can say that the men are old is taken into a consider. Why? Because see the young man of course will go and fight the enemy and the old man will have to be taken to a safe location. And see when you see that this particular reading then you can say that the sentence is old man and woman taken to a safe location. But see in this case the young man always always would fight the enemy. So here I can say that in the reading man are old is taken into consider, right? The men are old are is taken into consider is known as the pragmatics, because in a syntactic was happened. See the previous two page that we have discussed, one is the semantic. In both the cases what happened, when I take this sentence old man and woman were taken to a safe location. So in that case what happened, in a syntactic analysis what happened, so here there is an ambiguity, right? Also, the ambiguity means old man and woman, old man and young woman, and old man and old woman. That thing is there. Now, in semantic, also giving the two possibilities. But in a pragmatic, what happened? Here, it derives the knowledge from the external common sense information, right? And according to that, it derives the knowledge, and according to that, the pragmatic says that both men and women being old, both men and women being old, and they've been taken to a safe location is less probable than the fact that only the men are old, right? And that's why in a pragmatic now, from the pragmatic now, it derived that old men were taken to a safe location because it is more probable than the both men and women being old. So this thing is done in a pragmatic, because in the previous two stage it giving the two possibility, but the pragmatic is derived the knowledge from the external common sense information, and based on that the pragmatic, right, says that in a pragmatic analysis, because of that information, that common sense information, the pragmatic say that both men and women being old, they have been taken to a safe location is less probable than the fact that only the men are old. Okay, so this is the concept of pragmatic, everyone. Now then, after the last step, that is discourse. So here you can say that the meaning of the sentence, the meaning of an individual sentence may depend on the sentence that precede it and may influence the meaning of the sentence that follow it. Now see, directly see this sentence everyone, in that you can understand कि John is sleeping, and the last one, that is he is lazy. So now listen, here in this case you can say that, see, the meaning of an individual sentence may depend on the sentence that precedes it. So, and may influence the meaning of the sentence they follow it. So here what the he represent, so here in this, in the discourse you can say that, and in discourse initially what we have discussed in a discourse analysis, all of you, it is a processing of connected of sentences. So here this he, you can say that it is he that depends on the sentence that precedes. Here he means, it indicating the he means it's about John. So this is all about discourse concept. Similarly, the another sentence like the Ferrari launched a new car model. Now the sentence is, this car is much better than the previous one. So here this that represents the Ferrari. Now the another sentence like, the Margaret invited Susan for a visit and she gave her a good lunch. So here the C represent the Margaret. So this thing is done in a what? Discourse. Okay. So these are the all phases of NLP, everyone. So listen. So this is all about the stages of NLP. So last 4 minutes left, everyone. So I will not start with the new topic. So in next lecture, I will explain you the statistical natural language processing. So in that, I will explain you the probability, how to find the probability of the sentence, how to count the number of word in a particular sentence, how to find the probability, biagram, unigram model, the different model we have discussed, Soundex algorithm that we have discussed. So that all these things that we will discuss in the next lecture. Okay, so we are ending our session over here. Thank you. Any doubt, everyone? If you have any doubt, then please ask me. Okay, so I'm ending my session. Thank you.
Good morning, students. Sunday, but a Friday schedule, right? 11 o'clock and BDA subject. Well, let me tell you, I'm running with very low resources today. Unfortunate enough. So if I may get disconnected after 40 minutes or so, uh, I mean if my mobile and laptop battery as well as network. So many concerns I have got today, unfortunately. Uh, So let's move on. Fine, it's a lecture, and in the previous lecture, if you remember, we have learned RPC, right? I demonstrated remote procedure call, and I'm sure it is there. Excuse me. So in yeah, so is there in your BDA conduit folder under hands-on? So we have lab 1 to 10 completed in a way. So these are extra topics, relevant topics. We don't have any number given to this, okay? But then the folders are there, RPC and message passing. We will touch message passing again maybe on Monday itself. Let me continue with other topics, relevant theoretical topics with respect to distributed computing. Know that we have described three algorithms with respect to distributed mutual exclusion, right? So you got to explore all of them, three algorithms, and let me just type the name so that you know that you have to only study these three algorithm. Distributed, I'm typing it, you may note down. Distributed mutual exclusion, okay, and the algorithm is Lamport. Then the another one was Mekwaz, Maekawa, maybe I might have typed it wrong, the name Mekwaz, and the third one was what was the third one? Oh, really? Uh, what was the third one? Okay, there was token based, right? Token based. So Lamport was let's say non-token based, and then Macwas was uh, quorum based, QUORAM, quorum based. Which one we studied last? The token based algorithm. What was the name? Because I know, many more algorithms. The name, is little bit difficult for me to remember. You also will be undergoing the same situation, but the last one was token based. Thank you, Jainik. Suzuki Kasami, right? Suzuki Kasami. Right, right. Thank you, Nidhi. And students, sorry about that. And I also expect you not to remember algorithms uh, uh, beyond your exam at least. But during your exam time, try to, I was, I think I would have told you, I was not having confident at all to remember names. That was one of the reason I didn't go for, MBBS, though I was getting grantinate seat in MBBS, that is year 1999. But I had impression that I would not be able to remember medicine names. And that was one silly reason I didn't choose medicines that time. And that's a belief actually which put you back, and still I'm having this belief that I'm not able to remember names. That's actually weakness, I would say. Anyways, somebody in the past told me that you have to relate or associate names to certain things. That maybe one way to remember names. I tried. You also see if it works for you. Anyways, we'll move on. So make sure you explore these three algorithms, okay? uh, whatever I have typed into the chat window. Fine. Uh, that will be definitely discussed and will be questioned in the exam also. Okay. So that was distributed mutual exclusions. Any questions so far with DME? Did it interest you? At least, did you learn something beyond plain operating system? Any questions so far with DME, distributor mutual exclusion? No. Okay. So please learn from examples also. There were examples in each three algorithm. In first one, we had a space-time diagram, and in second and third, in second, we'll need little bit of quorum creation at least, and then in token base, we had data structures described the token itself. And interestingly, let me ask you this question. So we know that there is no shared memory amongst all the computer participating in the network like cluster. So where does token reside? If there is no shared memory, and as there has to be only one unique token, where does token reside? The question is this. Can someone answer? That's a token-based algorithm, the last which when we talked. If you have understood, you can try answering this. Where does token reside? As there is no shared memory, and still, we need a unique token, kind of globally, right? Token is kind of global, kind of, I'm saying. So where does it reside? I mean, yes, yes. So when I say token, uh, token has data token data structure has, if you remember, it has a queue for uh, maintaining all those sites who are about to request, and another one was an array, if you remember, an array. It was named as LN, if you remember. So token has this information. That what token means for us. It is nothing but set of information. Okay, right. So it's like digital token. You can say like digital token. Okay. So the question is, where does it reside? So Jaimin says at every machine. Now at every machine. So let's say there are 10 machines, then there'll be 10 tokens. I mean, what do you mean, Jaimin? Can you describe what you are trying to convey? I repeat, if there are 10 machines, and if you are saying at every machine, will there be 10 tokens, or how will it work? You are right in a way, but you have to still describe. Okay, if I assume in one direction, you are wrong. If I assume in other direction, you're right. So that you have to give more details. What do you mean by at every machine? You may be typing or may not want to answer. So others, any idea where does token reside? Okay, so see, every machine will have their own primary memory, right? And it can definitely hold data structure, right? We know data structure now, they are hold into primary memory, right? When they are persisted, it talks about the secondary memory, which is hard disk, right? So right. So basically token has, so there is no shared memory like global. So it has to be there somewhere in some individual machine's primary memory. And yeah, it makes sense, Maliha, you are right. The current machine which is accessing the CS or which has completed just now accessing the CS before passing it to anyone else, so the token will be with any one of the machine. Okay, you're right. The token actually resides in the primary memory of any one of the machine. In the beginning, it will be randomly chosen some one machine, and at that time token will be at rest or like token at idle token. Okay, but then whenever someone will want to execute CS, token will be passed to that site. So then by the time in between, token will be in the transit, I mean in the channel, network channel, right? And then once it is received on the other side, and when that site confirms that it has received the token, now that site will keep the token with it, I mean the data structure in its primary memory. So if you just imagine that token is something which any individual site will have, then where will it have? In its in primary memory. Yes. So Maliha, you are right. The current machine which is accessing the CS, or you can also say which has idle token. That may be the case once it finished the execution of CS and nobody else is requesting. At that time also, it will retain that token data structure into its memory, or maybe when the computer just started and randomly one site is given the token. So at that time again, it will be like token at idle token at rest, right? So that in those scenario, but we now understand, right? What is token? It is nothing but a data structure information. It resides into the primary memory of a computer which holds the token, and then it will, as I described. Hopefully that made some sense to you, right? So we are moving on to other topics. Let's just see. Okay, so I'm gonna share my screen from mobile only today. Uh, I'm sorry about that. For a better, situation, I actually moved from one to other place, but then the bad luck followed, and this morning 8 a.m. to 1 p.m. we don't have power supply, and it's unfortunate, but whatever it is. Okay, fine. So I'll be sharing this PDF with you. Okay, maybe later tonight. So what am I going to discuss now? We have already talked about introduction to distributed systems. We have talked about design issues, right? We have talked about distributed mutual exclusion, right? Now we are going to talk about uh, let me just take another introduction very quickly, and then we'll move on. So it is actually taken from the distributed computing subject itself, and there were books to refer. Okay, and the objective was to discuss advanced types of operating system, right, which involves a distributed operating system, then multiprocessor, real-time database operating system, etc. And you were supposed to say, right now we are describing part of the stuff. You still want to describe and learn so many more things, which has to do with memory, then processes, file system, disk management, IO management, right? All those things what you have learned in your independent operating system, those all have to be explored with respect to distributed system also. We will not touch each and every details, but we will try learning a few things which are important. Okay, so uh, introduction, right? Why do we need advanced operating system? We all know that it is the need of time where resources are actually distributed, right? High speed computing we want. Somebody yesterday mentioned, one of the student, that he's going to attend one event with Oracle. The word was HPC, and that HPC actually is for high performance computing. Okay, the short form or acronym HPC is actually for high performance computing, and it has originally it had to do with supercomputers, but nowadays it is also advertently used with distributed systems. Okay. Oh my goodness, what happened? Okay. So see, there are enormously complex design issues. I mean, that's what we are after. Okay, we are after exploring the design issues and their complexity, and maybe learning some solutions out of them. Okay, so network operating system, which was a beginning part, it was designed primarily to support workstations like personal computer that are connected to a local area network. And LAN versus WAN, I believe you know that, right? LAN versus WAN, right? A network operating system provides printing, sharing, common file system. Come on, this is ridiculous. Common file system and database sharing, etc. So I'm not certain, have you ever used a printer, shared printer in the network? So please learn that if you have not learned such small things. It's nothing, I mean, you can think of exploring networking topics, and you can actually share resources like printer, files, right, etc. Right? Oh my goodness, my daughter is troubling family. Wait, I'll close the door. If I close the door, there is less air circulation. Oh my goodness. Hold a minute there. So looks like nature is really after all of us. It wants to take over, though we are part of the nature, but uh, we actually have maybe gone beyond the, you know, okay, humanity. Fine. All right, let's move on. So there was some discussion on types of advanced operating systems. Okay, and people actually do design hardware, and based on the application requirements, there are various operating systems explored. But then I think there was a simple diagram. Yeah, this is a little simple diagram. It is actually talking about types of advanced operating systems. Which were actually architecture driven or application driven. And one of you please confirm that we are connected. I know we are, but hello. Yes, we are connected, right? Yeah, thank you. So this is a simple diagram maybe, but just you know about it. Types of advanced operating systems. They are actually one from architecture driven and another is like application driven. Now we know what is the difference, right? Architecture driven as well as application. So if we talk about application driven, if you are required to deal with ACID property, or at least you need transactions, or at least you are required to persist data. Doesn't matter whether it is acid way or base way, but if you're required to persist the data, that's one of the thing what we say database, right? So application driven was database system. Ilansi, you sit and listen, okay? I'm listening. Fine. So, and the other one was real-time systems. I'm not certain the embedded systems any of you got chance to explore, but embedded systems you might have at least heard about it, right? So that is one type of operating system developed, particularly application driven, right? So that's the right-hand side part. We are not going to describe it or discuss it, but the left-hand side part, when architecture driven, right? We needed more storage and more processing, and hence when supercomputing started exploring, like people started exploring supercomputing, and there was actually the multi-processor systems. Even a single computer now, that it has dual core, quad core, and like likewise. So there was multi-processor system. But then something what we are describing and we are utilizing is distributed systems, right? So distributed systems has to do with big data and analytics. The reason being, enormous amount of data and a huge amount of processing required. Fine. So distributed operating systems, we are aware all these things, right? It's just that I had that one diagram to discuss, so I thought I should talk to you on this. It's all same thing. Fine. So is from this particular slide, from this particular slide, importantly is a simple topic, and which is nothing but this particular diagram. Okay, and just that is also just to so that fine. Okay, so let's move on to the new chapter, in a way, which was from book. It was the fifth chapter, I think. It was the logical time and global states. uh, and we've been talking about this, if you remember, right? We've been talking about, there is no shared memory, and because of which there is no, global state known to each and every people. I mean, if for example, there is no common platform, or for example, let's say there is no common WhatsApp group, then all those 10 friends will really not know everyone's complete status, right? So imagine you have created this WhatsApp group of 10 people, and one guy will send message to the WhatsApp group, and we understand that, oh, okay, everyone knows it. And likewise, some other guy sends a message of his own status, and again, everyone knows it. But imagine there is no WhatsApp group of those 10 people. WhatsApp group is very much like a common shared memory, for example. But then learn that with respect to distributed systems, there is no such common shared memory. The reason being, even in the past, people tried to have client server approach, where server is considered to be a common entity, but it also had, limits, and, the limit will be its own architecture, the, memory as well as the processor. right? So and that's like single point of failure, single point of failure, right? Bottleneck. So those all things what we already know, and that's what is leading us to learn that there is no global state. There is no global state available because of unavailability of shared memory. So that's one thing. And the other thing is all of these computers are actually remotely connected via network, and hence they are not sharing the clock. Now, first thing first, to understand clock is actually the power supply to start with, and then uh, the plus 5 volt and maybe minus 5 volt. I'm not very good at understanding those things, but Niranshi, we keep silence, right? So Uh, yeah, so starting with the clock, uh, the very original thing maybe you would have learned from your third semester or somewhere. Nowadays there are less electronic subjects in our stream, but then when they were there, we were actually having, or we were even learning more about what is a clock, etc. But for us, if you say uh, bit one or bit zero, uh, we understand like digital number like one or zero, right? And we know that it is stored in the memory. But you should also actually explore, and maybe Professor Pandav helped during the fellowship to explore all those things, how those information is being really retained or stored, right? So what I'm kind of aware, or I learned in my time was, kind of some kind of wave where if it is a positive, we say one, and if it is a negative, we say zero. So some kind of, a mechanism, physical media where, some kind of indication will actually be interpreted as bit one or bit zero. I mean, data bit one or data bit zero. Likewise, like fourth. So, and let me tell you one more thing. In our second sem also, we tried developing just a simple graphical clock. I repeat, just a simple mini project, a graphical clock, like a wall clock, okay, and using C language and C graphics. You might not have got chance to explore that, but in time 2000, I mean, we were exploring it. C programming language and graphics, okay, and a very simple project. Let's say I would just try to develop a wall clock. So on my computer, it will look like a wall clock, and there will be hour hand, minute hand, and maybe second hand. Seconds hand, I don't know how to pronounce. But then, uh, how many of you have tried that? I mean, have you ever thought of doing this simple project, displaying a wall clock? Maybe not. But now let me tell you that itself is a challenge. Okay, even just showing a clock, it looks like what a big deal. Read the system time and display, right? But then, if you will do and if you will go in depth, you will realize there are concerns. Okay, and that's what is all about. I mean, from the top, it always looks simpler, but then when you go in depth, you realize that there are complexities and they have been handled with some or other algorithmic logic. Okay, so I tell you what was happening when I would say I, because I myself did that experiment in second sem of mine. Okay, so when I developed that C language graphical user interface wall clock, when I would say run the program, it would literally display, a circle, colored circle, and background filled with some another color, and maybe hour hand and minute hand. And if you might have ever heard about this, there were like a function called delay, DELAY, and there was another function called sleep, 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 likewise like four. Okay, so initially I just learned, let's say, delay function. Then I thought like delay, and maybe it was taking in the bracket number of milliseconds. I don't remember exactly. There's 1,000. If I say delay and 1,000, what was the idea? Just take the system time, then accordingly count the, where should be the hour hand and minute hand and the second, etc. Okay, first graphics display it, then have delay of 1,000 milliseconds, and then take this system time again, or just do +1, and then maybe I would not have done seconds hand. I would just have minute and hour hand. I'm not certain right now. But then display again. I mean, refresh the screen again, so it will show the next minute, and likewise like fourth. So we felt like, oh, it's working, it's working. But you know what happened? If we keep the program up and running, after a while, in the original wall clock, physical or mechanical wall clock, it would be, let's say, exactly 11 and 25. But in our computer wall clock, our own developed program, it would sometimes show 11 and 22 or 11 and 20, etc. I mean, it was falling back. Now, can you think why it may fall back? Uh, if I am not, if I'm just doing plus plus etc., it will fall back. For example, if I may be reading the current system time every minute and then do plus one, then it may fall ahead, something on those lines. Okay, can you think why that might happen? I mean, that's a simple small wall clock project actually is also challenging to do. And it was 2000, I was, let's say, maybe it was 1999, whatever, first year. So our whatever knowledge I would have at that time, I would have applied. But then we faced this issue. I mean, can you think why would that happen? I mean, does it make some sense? Why would it fall back or maybe fall ahead? uh, so then instead of delay, we thought like sleep is better. Uh, so we kind of tweaked one function to other function, and still we were not able to get exactly what was expected. And I would say I had to drop that project because further semesters and further subjects. And later on, actually, you should actually learn this part. It might fall back or go beyond, because there'll be always content switching happening. When you what exact time you will sleep. For example, exactly 1,000 seconds you sleep, and then you do plus one. That means that plus one itself is taking little bit of time every single minute. Over the period of time, you will be actually falling back, or going beyond. So you think of what concerns I'm talking, you think of it. Okay, but then even managing a single time is difficulty, is challenging. Okay, and you might have heard about network time servers. Okay, so when you are in network, maybe you might have seen some Linux computers, they may be falling off or so. Actually, there is something called network time protocol also developed to synchronize every other's timing part. Okay, network time protocol. There are so many things. Even the time management itself is a big deal. Fine, but that has to do with the date, the clock, the date and time. I mean, date and time. Okay. Otherwise, the clock you may understand as simple, like the power supply to start with. And all these computers which are remote, they have their own different power supply. At least one, at least a single computer having four processors, then it is having a common power supply. That means it is having a common clock. Okay. But then distributed systems like remote computers, they all will have their own power supply, the clock power supply, when we say. Okay. Anyways, so to actually tell you the you know even on a single computer, which event happened when, if you want to keep track of those things, it is difficult because of the concerns I mentioned, right? Then when we come to distributed computing, which event happened when, and because of the failures and the network delays, etc., uh, uh, you will never have a complete observation, you can say, like global state or the time itself. How will you really confirm that what time it is now? Okay. And then time doesn't mean just the system time. It's actually the the state time, I would just say state time. Okay, which is also named logical time. So how does it work? I mean, what brought the solution? So the solution is like every single thing will be considered as an event. I repeat, every single damned small identity or unit thing will be considered as an event, and it will be having a logical time uh, at that particular moment. So let's say when we just started the cluster, and the first event is termed to be logical time 1, then the second event is termed to be logical time 2, then the third event is termed to be logical time 3. So, and let's say there is actually 10 minutes, for example, between third event and the fourth event. So the event number third is actually having a logical time 3, And if even though there is 10 minutes in between, but the fourth event is actually considered to be logical time 4 only. I hope you are getting what I'm trying to convey when I say logical time. Okay, logical time is not, your date and time likewise thing. No, it is not. Of course, timestamp will be used for, implementation sake, but theory sake, you understand that logical time is nothing but every single damn event, whenever it happens, you just think like it is in universe. Any events are happening in universe, one after another. Those events, if they happen, okay, they will be given a logical time number. And then how will that happen? Who will give that number? All those things are still, need to be explored. And you may say, like in the universe, at any single point in time, two events also can happen. I mean, that's what's happening. I mean, in the universe is possible, right? So that will be called as concurrent events also, which is described going forward. Okay, so know that this is all talked about events, and event when it happen, it will be given a logical time. And logical time is not like date and time, minutes and hours and all. No, it is just a logical time, which indicates which event happened when. So when I say logical time 5, event 5 happened, for example, and if you tell me, how about event 3? Then I ask you, what time, logical time was it? You say event 3. I mean, logical time 3. Then I would judge that event 3 would have happened before event 5, because the logical time associated with event 3 is 3 for versus with event 5 is 5. And when I say event 3 and 5, they are, I'm assuming them names. The names can be anything, or process IDs, excuse me, process IDs, or event IDs can be anything. But then I hope when we are starting to talk about logical time, I hope that makes some sense. Let's go ahead with more description. So a DS is a collection of computers. What we know, they are spatially separated and do not share a common memory. We know all those things. Processes executing on these computers communicate with one another by exchanging messages over communication channels. We know that the messages are delivered after an arbitrary. This arbitrary is important. You know that messages might not be, because of multiple routes. Sometimes they may take this route, and traffic, etc. The transmission delay will be arbitrary, and it is actually the networking and electronic communications, part of it, which again we may not be able to understand completely. One day I was asking to one of the faculty that if we have designed, what do you really mean by loss of a message? I mean, how is it possible? I mean, see, if I have designed a courier service like FedEx, and someone says there was a loss of packet, I would say, really? How come? I mean, I have designed this complete, FedEx courier service, and you are saying loss of package? Really? I mean, I just cannot understand why would that happen, loss of packet. But in network, very similar to that, if you imagine, engineers, scientists have designed this, networking service, right? Very much like a FedEx, packets are moving from here to there, and we still hear that there was a loss of packet. We would say, oh my goodness, I mean, what are the reasons? I mean, how would that happen? We have designed the system like FedEx, and loss of packet, really? I mean, how? I mean, it's beyond my understanding. Honestly, I'm telling you, okay? But then there is real, okay? So you may explore, I mean, whatever is your understanding, but that's all, contributes to the arbitrary transmission delay, right? And the complexity of distributed system requirements. Uh, so the inherent limitations of distributed systems is the absence of global clock, no system-wide common clock. Solution is, system-wide common clocks, or synchronized clocks, right? But then there is always a drift, uh, you know, uh, as I talked about, the clocks may fall back. There has to be synchronized, and you may explore network time protocol. Okay, you may explore it. How does it work? Okay, but I'm moving on. Impact of absence of global time. What is happening because you don't have the global time? The scheduling process. When you say request arrival, if you remember your fifth semester arrival, you might have done some examples on first in first out, FIFO, or any of the scheduling algorithm, and you might have done examples where the request time arrival time will be given, and based on which you will solve that example in your fifth sem operating subject, right? But now here there is no time. I mean, how do we judge the arrival time, etc., right? So process scheduling request arrival time is important, but then temporal,
Hello, sir.
yes.
Sorry to interrupt you, but your screen is not visible.
Oh, no problem. Good that you interrupted. I don't know how would that happen, but let me just. I really don't know how would that happen. I mean, did I touch anything or what? I'm sorry. No problem. Thank you. Uh, so mostly whatever I described was very much like my experience I shared with you, and I wanted you to learn from you know uh, uh, that discussion. Anyways, I was sharing this particular PDF file, which is just now started. Okay, we talked about the inherent limitations of DS, which is the absence of global clock, right? And then I talked about this scheduling, process scheduling, etc. Right? It is difficult to reason about the temporal order of events. Now, this is actually leading to some mathematics like distributed, what was that? District maths. You might have heard about few of these terms like temporal order of events and all. How many of you have heard about this temporal order kind of things, maybe in your gate preparation or maybe in your discrete mathematics? Or let me move on for now, then I'll ask you. Okay, and you don't have a shared memory also, so you don't have a complete state. And absence of shared memory, I have already given you analogy like absence of a global, WhatsApp group, right? If you don't have absence, if you don't have a WhatsApp group, you will not know the state of those members, 10 members, for example. So up to date state of entire system is not available to individual process, and that's because of absence of shared memory. It is important for deciding systems behavior, debugging, recovery from failures, etc. We definitely need to know the complete state, which is also called global state. So it is difficult to obtain the coherent global state. And the reason is, we only have messaging as one of the solution and RPC as another. There is no, satellite kind of thing which will be able to capture everything from the Earth. And that too, there is nothing like central entity here. Anyways, so this is actually a few definition here, and it may not make much sense. If those who understand the meaning of coherent, you have these two definition here, coherent view and complete view or global state. So a view of a system is said to be coherent if all the observations of different processes are made at the same physical time. Uh, that's the definition. I would not go in depth of that. But the complete view or the global state is actually a view encompasses the local views at all the computers and any messages that are in transit in the DS. Okay, now you understand this. When I say global state, what does it mean? It means all the local states plus the messages in the transit. And that's actually your distributed system. I repeat, all the local data structures with all the computers. Moreover, the network status, where are the messages? Okay, that actually consists the global state with respect to distributed system. So what is global state in distributed system? It is nothing but the complete view of all the local states and the messages they are there in the transit. That consists the global state. So I believe you understand what does global state mean, okay, which is also called complete view. I would not take this example because there is no description available there. Uh, so Lampert, one of the scientists, you would explore it. He's still there, I think. Uh, he actually, provided this solution called Lampert's logical clock, and it is widely used based on which many more things been, devised. Um, execution of processes, they are characterized by sequence of events. If you remember, I described before starting this chapter, which is nothing but a sequence of events. Everything is considered to be an event, and there will be sequence of events, right? Execution of procedure could be one event, or execution of instructions could be one event. How small you want to define an event, that is up to the designers, but sending a message can also be one event, or receiving a message can also be one event. Okay. So how finer grain, I mean, how small atomic thing you need, that is up to you. But more atomic is more better as single individual event. So Lamport has actually devised this theory called happened before relation, and this is very much to your discrete mathematics. You might see this in your gate exam also. Uh, so what it has to say, happened before relation. What does it mean? It captures the causal dependencies between events. Causal is like, cause. It has to, it's not casual. I don't want to read it as a casual. I think the spelling looks same, but then I want to read it as causal. I think the spelling is mistyped. I would have to check on that. My impression was I used to read it as causal because there is like cause relationship, like because, cause relationship. It's not, please cross check this spelling and its meaning, but I still want to stay with the understanding of, cause. Cause means, something happened likewise. Okay. Uh, so A arrow B, what it mean? If A and B are events in the same process, so A has happened before B. That's what A arrow B mean. I repeat, event A has happened before event B. That does A arrow B mean? Now, A arrow B, if A event of sending a message M in a process A, and B is the event of receipt of the same message M by another process. Again, you will say A arrow B. Again, there will be limitation of this. We may explore that. But again, if there is like A arrow B and B arrow C, you can judge there will be A arrow C, right, which is nothing but a transitive relationship. So these are very much similar to your discrete mathematics discussions, whatever you might have already learned in the past. Uh, so we also know that past events, they influence future events, and this influence among causally. Uh, See here, the spelling is correct. I think the above one is CASU. That is incorrect. Okay, this spelling CASUAL casual is incorrect because I'm certain it is CAUSALLY causal. Okay, because it's like because cause. Okay, causally related events is referred to as causal effects. Uh, it should be again effects, but anyways, I should check this. Fine. So event A causally affects event B if A arrow B. Okay, that is what it means. So two distinct event A and B are said to be concurrent. Yeah, this is about concurrent events. If A and B and B and A are false. I mean, okay, there is an and relationship. So if you cannot say that A happened before B, or if you cannot say that B happened before A, you cannot say both of them. That means you have to say A happened at the same time as B happened, and you would then say it is a concurrent event. So the two vertical lines, they actually denote a, that A happened concurrently with B. Uh, so for any two events, A and B in the system, either you can say that A happened before B, or you can say B happened. Nilansi, please keep silence. Diko, you can say B happened before A, or you say A concurrently happened with B. Okay, or you can say A and B happened concurrently. So the space time diagram, please learn this technical word, space time diagram. You will have to use it in your exam or maybe in your future when you deal with distributed operating system. One of you please confirm that we are connected again. 58 students, please, one of you please confirm we are connected. Thank you, Maliha. You know the concerns, right? If we are disconnected, I will be just talking for long and will not be useful. Anyways, so space-time diagram is actually one way to represent, events and their causal effects and ordering, etc. Okay, so we will not go in detail of each and every of these, but space-time diagram. We already have described this in distributed mutual exclusion, if you remember, right? So Lampert's logical clock is actually, there is a clock CI. So this is the definition of logical clock. Okay, now there are some questions. Let me read the questions so that I can describe that if they are relevant here. Vivek, uh, Vivek, how we manage logical time across a cluster? How a machine knows about logical time? Is it fine? So Vivek, of course, there are questions and there are no straightforward answers immediately. You have to learn so many things around, and then only you will come to a decision or you will come to an understanding. That's what we are after. Okay, I know I'm not giving you clear answer, but this is not possible because there are so many more things you have to visualize to completely understand that there is something called logical clock. Okay, so I'm trying my best to give you the old things and new things, and my experiences, and maybe your generation experiences, right? I'm trying to combine so that you at least can, excuse me, learn better. uh, and it may happen even after all these efforts, you will still have blurry understanding, or a fuzzy understanding, and that's still okay to start with, I would just say, because it is your seventh sem. uh, See, as I said, in my second sem, I would not be able to judge why completely that would happen, because there will lot many things, unless somebody else points me or I learn from some sources. Okay. uh, Anyways, fine. I'll move on. Let's talk about Lampert's logical clock. Little bit of definition here. There is a clock Ci at each process Pi in the system. Now, before I start this description, remember when we started talking about token, we really couldn't understand what will be token completely, right? I mean, but I believe once we understood that token-based algorithm, and when we understood those, data structures a bit, and when we finally took that example where, if you remember, I described, the token queues as well as those, entries into like 123 or 35 or some certain entries into those information, we had better idea that, oh, what token might be now, right? And even today's lecture, when we started and described, we now understand little better what is token. And that what actually happened to me, or maybe it will happen to most of us when we were in first sem, and when the faculty was doing I equal to I plus 1, right? If you don't really understand what is I mean, uh, you have to know that it is a memory, it will hold information, and it is having a name called variable I. When I want to read it, I will use I. When I want to write it, I will also use I. And it has L value and R value. Unless you go in depth gradually, you won't be able to understand more. And we still need to learn. I mean, though after 20 or years, there are still complexities out there which we might not have yet explored, right? But that's how it is. I mean, that's how it works. uh, you have to keep going in depth, right? So why did I tell you that I equal to I plus 1 and all? The reason being, I actually was thinking that in mathematics, nowhere I have seen, phi equal to 6. This professor is literally, mad, and he's trying to tell me phi is equal to 6. How is that possible? You know, something on those lines. I mean, that's also one perception somebody can think, right? I is I plus 1, and then professor will say I is phi. Then we think like, okay, phi plus 1, 6, phi equal to 6. Come on, man, are you mad? Phi equal to 6. Which mathematics tell this, right? I mean, we would think like that. But then we will have to learn that equal to is not actually the comparison. It is actually the assignment. And that's how we grow, right? So here, this all Lampert's logical clock. Uh, the question to Vivek, you let's read this. Then it will make little of sense that with the absence of global memory and common power supply, like the logical clock. I mean the physical clock. How the logical clock is implemented. Here it is. There is a clock Ci at each process Pi in the system. So see, there is actually every process maintains their own clock, and their clocks, they are called Ci clock. I mean, at ith system, the clock is saved Ci. So let's say there are 10 systems, then every one will have their own C1, C2, C3 like clocks. Now, what exactly clock mean? Again, it's gonna be data structure only, but we have to think what all things we will need to store into it if we go in depth. Understand? What is a clock? It's nothing but a data structure. I mean, that's what you have to understand. When we say I equal to I plus 1, we have to understand there is nothing but a variable, and it is attached with a memory, likewise like code. So there is a clock Ci at each process Pi in the system, right? And we at least now understand what it mean by process, so we can at least think of it. But what is a clock, we still don't know, but let's learn. Okay, so the clock ci can be thought of as a function. Okay, so it's a data structure or a function. So here he says a function. Now when you say function, again function will have local variables, so some information is definitely going to be there, right? I mean, some memory is definitely going to be there, right? So the function that assigns a number ci of A to any event A, called the timestamp of event A at PI. I mean process I. I mean, it's little long to understand, and there are more things to learn. So you can say clock CI is a function, okay? And what will it do? It will actually assign a number CI of A, I mean some number, to certain event. Okay, and it will basically is very much like a sequencer. Okay, it's very much like assigning a number, but to assign itself it will have to remember past numbers, for example. Yes or no? So call the timestamp of event A at PI. Now fine, so it actually behind the scene also uses the timestamp, okay, uh, for generating that number. So know that the timestamp and the assigned numbers are two different things. It's not directly assigning the timestamp. It is saying it is assigning the number, okay, and that may be the direct timestamp, or that may be something else also. To give you one example or analogy here, even in our fifth sem, we were doing other mini projects from some book called Numericals in C. So we would have to literally go into library for first week and then read this book and choose the project. It would have various mathematical algorithms and problem statements, and we would have to develop a program for that. And the one of the team member, my friend only, will actually have some of his input in our class maybe next week. Uh, he's there in Bloomberg, USA, last from I think 13, 14 years. I'll give you more discussion about him. But he actually chose this project called random number generator. Can you think a project to write a program which generates a random number? And if someone says, what is the output of your program or project, you will say random. Really, does it make sense to write a project which generates a random number? And because you guys are using it, now, but in that time it was also something like new, and something which is not very common to understand. Okay, if you tell someone that, oh, my program gives random output every time, somebody will laugh at you. But that's what's the actual requirement, right? And you guys very smoothly use this array and d function in your C language, but it was not just to use array and d function and display it. No, it was to develop the logic of array and d function itself. Now, can you think how will you write that program if you have to write it? Generate a random function, random number. Now, I mean, that itself is algorithm. Okay, there are a lot of algorithms involved in generating a random number itself. And one thing, actually, there is something called salt and more. Okay, so timestamp is used as one of the ingredient of generating random number, because if you see this property random number, it would be random. I mean change, right? And what is the only thing which is changing always in our system, in our computer system? Can you answer that? I would really expect one answer from you. Can you guys think anything which is always changing in our computer system? Yes, Atis, you got you right. Right? The time, other things will be definitely there, but the time is the one thing which always changes, right? And that's why it was used as one of the ingredient for the algorithms of random number generator itself. Okay, and Vivek, yes, see, the things are, if you go in that, if you are part of the team which has to devise solutions, you will have to put your head into wall, you'll have to be upside down, and you'll have to think and come up with solutions. It may initially sound silly or doesn't make sense, etc., but it might come. That's what is about, utilizing brain, right? So coming back to the topic, again here, of course, the timestamp is one of the ingredient behind the logical clock, right? The Lampert's logical clock is one of the ingredient. So why I told you all the complete story of random number generator, the reason being, we are thinking how to really develop logical clock. We know limitations, we still want to come up with a clock, okay, which can at least tell me a global state of distributed system, like which event happened when, right? So that's all. I mean, there are a lot of more things. It's been years. This is, been done. We are trying to understand it, and it has no relation with physical time actually. Okay. Indirectly, you may think it might have because the timestamp was one of the ingredient, but uh, if you just say, is there a direct relationship, then the answer is no. Okay. And it is actually the Lampert's logical clock is nothing but a monotonically increasing values. Okay. Uh, and then actually, see, students, please honestly tell me, does it interest you whatever we are describing? Because these are all, very important things to understand. I mean, they will let you, start thinking into uh, different, scenarios. And believe me, I'm not just passing time, or it's not a filler. Okay. Uh, I mean it. Okay. Uh, okay. Thank you, Maliha and Vivek and others. Please bear with me if that sometime feel boring and all. But discussion is the best solution to learn about things which are there. And I'm bringing all my experience together and try, kind of discussing with you whatever possible best. Anyways. Moving on, definitely. So Lampert's logical clock, the theory definition, at least we little bit understood here, right? And the condition satisfied by the system of clocks, if again there'll be things to move on. Let's just read. If A B, then CA is less than CB. So C is actually that particular CIA. You see that how it is defined, the clock CI, okay, and the clock CI is actually at each process PI in the system. So now in one system, you might have multiple processes, and hence at one system, you will actually have multiple CIs. Does it make sense? CI is, okay, there actually, so there are more things to think of, okay. So uh, this clock, the local clock, is actually attached to the local process, and you may have multiple processes locally, and hence you may have multiple local clocks attached with each of those processes. So there are more things to come up. Okay, for now, understand that everything is connected. I mean, I say local clock, then you should ask whether it is one or more, because the clock is actually attached with the process, right? So there are more things to learn about. Let's just keep learning. Then we will, we may have a better picture. I would never say we will have complete picture, because it's always gonna be, you read 5 times. The sixth time you read, you will still learn something new out of it. Okay. If A arrow B, then CA is less than CB. At least we know that A arrow B, theoretically, we wanted to mean that A happened before B. And if so, of course, the CA has to be less than CB, the monotonically increasing value, that CA has to be less than CB, because we have device like monotonically increasing, right? The arrow relation can be realized by using the logical clocks if the following two conditions are met. The first is, for any two events A and B in a process Pi, if if A occurs before B, then CIA is less than CIB. That makes sense with respect to process Pi. Imagine process Pi, let's say, opened a file, that's event A, and then started writing into a file that is, let's say, event B. And we would think like those are two events pertaining to process PI on a system, whatever SI, for example. And we may say like CIA has to be CIB, which is nothing but a monotonically increasing value. Okay. If A is the event of sending a message M in the process Pi, and B is the event of receiving the sending same message M at the process Pj. So the complexity is increasing here. Initially, we just thought of single process, but then this second option says there are two separate processes, Pi and Pj. Okay, and here CIA is less than CJB, and I mean there's still we are talking global, I mean logical time clock. Okay, so let's move on. I mean, I know it didn't complete the explanation. What is the time now? Oh goodness, I could see, oh, it's exactly 12. I could see the wall clock. I literally saw the wall clock just now. It's exactly 12. Okay, so let me conclude. So there will be implementation rules, right? We'll see. So there is actually, the max, if you may think, this max, if you remember, we had certain max-like function applicable into some other algorithm, if you remember. So this has to do with, synchronization of local and global. See this message passing and all this, if you remember the synchronization of token and the local state, there was the max which was used, if you remember. So there's the same logic applied here also. Okay. Because there's no common information, common memory. Everyone is synchronizing what I know latest, I give it to you. What you know latest, you give it to me. That's way we know both of us are on the same page. That's very much like this max logic there. Fine, we'll take up again. We'll continue. We'll continue further. I'll have to, describe limitations of Lampert's logical clock. You please think what might be limitations of Lampert's logical clock. Okay, that will be the last topic we'll describe with respect to global state. Fine. Okay, I'll stop here. Let me just see quickly if there are any recent questions. Uh, Okay, not as of now. We'll continue, maybe two more lectures into this. And if there are 2 weeks left, next week, two more lectures, we may still continue distributed computing fundamentals. But then last week, I will try to come up with some analytics part also. Okay, thank you very much, students, for your time. And over to you, next faculty.
So good afternoon all, and I hope you all are ready for this backpropagation. And so this might be a very important lecture for this machine learning as well as from the deep learning's perspective, right? And the story so far, we know the architecture, we know the feed forward neural network architecture, we know what exactly the dense connection means, and we also know that what we are supposed to derive, right? We needs to find this gradient. And to have that gradient, we need to have the partial derivative with respect to all the weights, right? And let's just quickly see what is the meaning of this three number. Let me just pick some random value. Let's say this 1 to n. So the meaning of this is this W1, this first one indicates it is related to the W1, where the W1 means weight between input and the first hidden layer. Fine. So that is the meaning of first one. 2, and the last one is n. Fine. So what was the meaning of this 2? It is a second neuron of the first hidden layer or the second neuron of input. Right. So always remember that the first number that we are considering, that is of the previous layer, right? And this n indicates the last neuron of the first hidden neuron, for the first hidden unit, or the first hidden layer, right? So if I want to represent this 1 to n, can I say that we are talking about the weight which is associated with this line? right? Where 1 means this W1, 2 means this X2, and the N means this last neuron in the first hidden layer. Right? And so on, we have learned what exactly the usage of this particular matrix, and we are supposed to find all these values, right? We are supposed to find the gradients, and to find the gradient we need to find all these partial derivatives, right? So that's what we have discussed so far. Now next, for the back propagation part, we need to identify two things. One is the loss function that we are supposed to use, because based on this loss function we'll apply the partial derivation, right? And the second is the computation of this partial derivation, or you can say the computation of the gradient itself, right? So we'll see both the problem one by one. First, let's discuss about the choice of this loss function, right? The output function and the loss function. So consider this particular diagram where you have a neural network with L-1 hidden layers, right? And we some notation, let's just recall the notations. The last layer, that is Lth layer, is our output layer, fine, and we have L-1 hidden layers in the given neural network, right? And assume the problem of identifying, or let's say to predict the rating, that, and for prediction purpose we have different agencies. Let's say we are considering the IMDb, then the RT rating, fine, and we have different values, right? So that is the simple problem which we have already observed in many different scenario, fine. But what we are interested to know, or what we are interested to learn over here, is what should be the best choice for the error, or you can say for the loss. So you have the correct rating value, you know the predicted rating value, right? So if you have the two values, so what should be the best choice of error or the loss function, right? So that is over here, fine. Whatever is your prediction, that is y hat, minus the actual value, that is y, fine. And now as you observed, we have three different values that we are supposed to predict, fine. So this exercise, that is y hat minus y, we have to repeat thrice, right? So that's why this j start from 1 up to 3, right? And once you repeat the highlighted portion, that is j start from 1 up to the 3, and the difference of the prediction and the actual value, that we are doing for a single example, and we have such n examples. And so one another summation, one other sigma, which start from I, which start from 1 up to the n, which is related to this, all the examples of my input data, fine. So this is the appropriate loss function whenever we have this kind of prediction. That is, we are supposed to predict some number, right? And for that number value, we know what exactly the correct number, and we have some predicted number, fine. So this square error loss will okay for that particular purpose. Now next, consider the classification problem, where as an input we have some image, right? Let's say it's an image of apple, fine, and as an output we are supposed to predict the correct class, that is let's say apple, mango, orange and banana. Out of them we are supposed to predict one value, so the correct answer that we know, that is 1, right? And in the prediction, what will you get, or what we expect in the prediction, right? So we expect the probability values, right? The probability distribution between these four classes, right? So that the total or the summation would be 1, fine. So whenever you want to have the prediction as a probability value, and you want to find the highest probability to label it as an correct class, or you can say to label it as a predicted class. So in this example, which should be the good loss function? Can we use the square error function once again? No, then what should be the appropriate function? The log loss, Right? So as it's a probability distribution, right? And one more thing, the output, we are going to use this particular function in output, right? And what's the name of this function? Just the cross entropy. So the loss will be the cross entropy. Now for the output, what's the name of this function? Is it known to us? Right, so that's a softmax, right? As we have this probability distribution, this function is the softmax function. Fine, and as you all know that the good choice of the loss function should be this cross entropy loss. Fine. So depend on the problem definition that we have on hand, we are supposed to choose appropriate loss function as well as depend on that particular problem definition, we should have the appropriate output function, right? Now, one thing that I want to observe, that we should observe over here before moving towards the next point, that is calculating the gradient. Whenever the yc is equals to 1, so if you consider the equation, right, the cross entropy loss, and we have also explored what exactly the meaning of this cross entropy, right? We have started with the entropy and then we have reached towards the cross entropy, and the reason why it is referred as a cross entropy is we have two terms associated, the yc which is the correct and this y hat c which is the predicted. Fine. So if you observe this particular example, so this yc, the value of yc is 1 if the c is equals to l, where l means the true label. Agree? And for rest of the cases, this yc is 0. Fine. So can I rewrite this equation as simply minus log of y hat l? To answer this, you must know what exactly the value of k right now. So can you tell me what will be the value of k for this example? 4, right? Because we know that the k means the actual number of class or the different classification values, possible classification values, right? So c starts from 1, 2, 3 and 4. Fine. So whenever c is equals to, let's say, 1, for this given example, what is the value of yc? C is equals to 1. So what will be the value of yc? Yc means the correct class value. So that is 1. If c is equals to 1, yc is also 1. So as this term is 1, what we have? Minus log of yc. Once again, y hat c. Fine. So for c is equals to 1, we have minus log of y hat c. Right. Whenever c is equals to 2, what is the value of yc? 0. Right. C is equals to 2. That means yc is 0. So this term is 0. So what will be this value? 0. And if you observe, for c is equals to 2 as well as for c is equals to 3, we have the same scenario. Sorry, 3 and 4, right? So this is c is equals to 2, this c is equals to 3, and this c is equals to 4. And for all these cases, the yc value is 0. So we do not have any term related to that particular terms, that particular values. Fine. So we only left with this term, that is minus log of yc. But let's say instead of c, if I write l over here, where l is a true class value, so you can say that it would be minus log of yl. And remember that we'll use this terminology. Small l means the true value, the true class value. And so in our case, small l equals to 1. That means we are referring this class, class number 1, for which the value is 1 itself. Is it clear? Because whenever you just write the c, that means the range. We are talking about the range. C start from 1, 2, 3 up to the k. Fine. So better I can write y1 over here, because this is the equation of minus log of y hat 1. Fine. But to be general, instead of 1, let's write L. And what should be the value of L? When L is a true class level, so whenever C is equals to L, then this will be the answer. And for rest of the data, it is actually 0. So this will be my final loss function. Are you fine up to this point, everyone? Minus log of y hat L. Right? And also remember that L means the correct class label or true class label, right? Because this we will use in the derivation. Fine. So if you have pen and paper, just note this down. This loss function, cross entropy loss, which eventually reach towards this minus log of y hat L. Fine. So we'll use it once again lateral. So one summary of this: if we have in output, if we have the real value, and versus if we have the probability value, then which should be the good choice of activation and which should be the good choice of loss function? Fine. So from previous two example, I think you all can able to identify these values. So let's say if we consider output as a real value, right? So that was our first example, the movie review. Fine. So output activation should be a linear function, right? And the loss function can be a square error loss, right? As we have discussed. And if it is probabilistic distribution, as we have seen in the previous example, where we are supposed to classify the fruit in one of the four category, so the output should be the softmax and your loss function should be the cross entropy. Fine. And in general, you can apply this logic with any kind of data majorly, but these are not only limited choice of output activation as well as the loss function, but widely used choice of these functions. Fine. So whenever you have the real value in output, then you can go with this choice, that is output activation linear and the loss function should be the square error. And similarly, you can check the choice for the probabilities. Fine. Okay, so now let's move towards this back propagation. So now we have the loss function ready, and now we want to have the partial derivation with respect to that loss function, and the partial derivation will consider for all the weights starting from the last layer up to the first layer. Fine. So let's answer this second question now. What should be your gradient, and how can we compute or how can we calculate the gradient value with bias as well as weight values? Fine. So for the calculation of gradient, just focus on a single term. Let's say this weight W112. Fine. So let's just quickly recap 112, where the first one means we are talking about the weight between input and the first hidden layer. Second one means, oh, it's yeah, the second one means this particular first neuron, fine, of the hidden layer. And the last two means the second neuron of the input. Is it the same notation that we have used previously? Reverse, right? So it should be 1 to 1. Fine. So this consider this as a 1 to 1. Fine. Where the second entity indicates this x2 and this last one indicates this particular one. Fine. So the point over here is, because it doesn't matter, right? We'll not going to use this further anyhow. So this is just for your understanding. So I will make this correction. It should be 1 to 1. Fine. Now to calculate this value, to calculate this gradient, what we are supposed to do, the partial derivation of the loss function with respect to this weight W 1 to 1. Right? This is not 1 1 2, it should be 1 to 1. Right. But how can we calculate that partial derivation? So to understand that, let's consider this simplest version. Let's assume this is our neural network where we just have one neuron at each layer, right? And there will be a one-to-one connection, right? So in this simplest version, let's try to see what should be the partial partial derivation chain, right? By applying the chain rule, how can we calculate the partial derivation? Fine. So let's just spend some moment on these notations, and let's recall what do you mean by this L theta. The loss, and we know that the loss value for this our problem is cross entropy loss, and for that we are considering that minus log of y hat L, and the y hat, or you can say your output, that is f of x. Fine. This is the layer L. So we have pre-activation value, that is a of L1, and the post-activation value. So what is the post-activation? What is the name of post-activation value? Yeah, that's a function, right? So, but the notation, pre-activation notation is a of L1. So what's the notation of post-activation? That is y hat, right? And the weight is W of L11. Fine. Then this second hidden layer, so this is, you can say, hidden layer number 1. This is hidden layer number 2. Fine. So for this second hidden layer, we have A21, which is post activation, and H21, which is sorry, A21, which is pre activation, and H21, which is post activation. Fine. And similarly, we have H11 and A11, right? And the input is X1. Right? So let's just consider a very simplest form of this particular neural network, where we have two hidden unit, and each unit is of one neuron only. Similarly, only one single output in a single output as well as single input neuron. Fine. So now let's move ahead. So as we have discussed previously, we are supposed to calculate this partial derivation of the loss function with respect to W111. That means we are talking about this particular value, W111. Fine. So there is no direct connection of this loss value which we are getting in the output and this W111, which is a weight between this X1 and the A1. But with the help of the chain rule, we can calculate that loss value. Fine. So to apply the chain rule, what you need to do, you have to start with this loss, that is L. Take the partial derivation of loss with respect to this value, and we know that that is the y hat. Fine. So the first is, we are taking the partial derivation of loss with y hat, right? And we are just using the chain rule, right? Next, partial derivation of this y hat with respect to this a of L11, right? So that means we are talking about this value, pre-activation of the output. Next, partial derivation of this a of L11 with respect to H21. That means this value, right? Then partial derivation of H21 with A21. Next, partial derivation of A21 with H11. And next, partial derivation of H11 with A11. Right, and finally we can have the partial derivation of this A11 with the weight, that is W111. Right, so likewise, using the chain rule, we can calculate the partial derivation of the loss with respect to the input weight, that is W111. Are we fine, everyone? Are you fine with this formula? binary classification, yes, no, where yes means 1. Okay, yes means yes. Fine. So now we have just considering the we have just considered the chain rule, right? We haven't calculated any of the partial derivations. Fine. Now I want to just reduce the size of this chain rule. So what I will do, instead of writing this all stuff, I'm writing it like this. Right? We're just compressing the chain rule. So if you observed what I have done, this term, that is partial derivation of your loss with respect to h11, I have just represented it something like this. Fine. Whenever you want to calculate the actual value, you have to expand it, right? So that once you expand it, it will be similar to this red data. Fine. And similarly, for this second part, we have represented it as this h11, the partial derivation of h11 with w111. So how many of you are compatible up to this point? Oh, how many of you, rather than how many of you are compatible? Is it clear? Fine. So just this short representation. Actually, we means the same thing, right? For the calculation, we have to calculate everything as it is. Fine. And in similar manner, if you want to calculate what should be the loss with respect to W21 and what should be the loss with respect to W of L11, you can see this formula. Right. So the first formula above this first green line that we have written for this W111. The second formula, it is for this W211 and the third one is for WL11, and that's what we want to calculate. Right? So we need to if we consider this network only, we need to calculate three things. One is partial derivation with respect to the output unit or the output weights, partial derivation with this hidden unit, and the partial derivation with this input unit. Right? And when we say input unit means the weight of that input unit. Right? So there are the tunable parameter. Comfortable? So next we'll see all this derivation one by one. So which one is the easiest one out of this WL11, W211 and W111? Which one is the easiest one? The last means in diagram last or in the equation last? L11, right? So we'll begin our discussion with this WL11 where we have a very small formula. Fine. And step by step we'll calculate it for the hidden unit as well as for the bias as well as the activation also. Fine. So now before going into the mathematical depth, let's just have the representation, the figure representation of what we are supposed to do. So we have this loss value that is minus log of y hat L. We'll go backward and we'll try to tune these parameters, right? Or you can say we'll try to tune the weights. Fine. So if we represent it in the if we represent it like a story, what you can say, we'll give it to we'll go to the output unit, right? This green neurons, where we'll just talk with the activation and we'll tell them that you have made a mistake, so just adjust your weight. Fine. But if you consider the case of activation, what exactly the activation? It have this WLHL WL H L minus 1 plus the bias term, and on that it has applied some function O, right? That is activation. So in our case, the activation that we are considering is the softmax, the final activation. And the loss that we have considered is this minus log y hat L, that is the cross entropy, right? So this dark green activation will take the responsibility at certain level, and it said that now I am just I have just calculated this value, so forward that particular updation or forward that weight updation to this light green part also, that is the second part. Fine. So we'll adjust that weight accordingly, and then once again the second part will say that I have done the calculation based on the activation, or you can say based on the output that I have received from this H2. Fine. So we'll go back to the H2, and the H2 once again forwarded it to the this A2, that is pre-activation of the second hidden layer, and so on. We'll reverse, or you can say we'll update the weight into the reverse direction. First we'll update the weight of output, then we'll update the weight of second hidden layer, then we'll update the weight of the first hidden layer, and then we'll update the weight between input and the first hidden layer. Fine. And in this manner we'll update the weights. Fine. And that's why it is referred as the back propagation, right? And as we have derived previously this chain rule, as we have seen this chain rule, so this, whenever you want to have the loss with respect to this W111, that is the first unit, how can you do that? First, loss with respect to the softmax, that is with respect to y hat with respect to A3. So this is all about the output unit, right? Similarly, if you consider the second part, that is all about the H2, that is the second hidden layer. The third part is related to the first hidden layer, and the last one is with this input, which is in between input and the first hidden layer. Fine. So likewise, we'll go back towards the first 10, or you can say towards this first weights. Fine. Now let's see it mathematically. So we'll see gradient with respect to the output, with respect to the hidden, and weight and the bias. Fine. And as we have discussed, since this first slide of this lecture, we'll focus on the cross entropy and the softmax output. And so keep this in mind: cross entropy loss and the softmax output. Fine. So let's begin. First, we'll discuss the weight, or you can say gradient, or the back propagation with respect to the output unit. Means we are interested in this red highlighted parts only. Fine. And later we'll see what will be the scenario with the hidden and the other layers. Right. Okay. So from this slide, if you are getting if you have some doubt in your mind, just ask the question at the same time, right? Because this will have some more mathematical depth. So first of all, our loss function L theta, that is minus log of WL, and we know that this L means this true class level, right? So whenever I say that true class level, and just think about the y hat. So y hat is a vector, is a scalar, or it's a matrix? It's a vector, right? So y hat is a combination of y1 hat, y2 hat, y3 hat up to yk hat, right? Up to yk hat. And this L is somewhere around in between y1 hat up to the yk hat. Agree? So what we will do, we will just focus on this y hat L, which is one instance, or you can say from this full vector, which is one single entity. And so this y1, y2, y3 up to yk. And assume that this y hat L is y3. Fine. So first we'll calculate the partial derivation with respect to this y3 only. Fine. And in general, rather than saying it as y3, we'll say partial derivation with respect to y hat L only. Right, which is, you can say, ith input. And then we'll expand it towards this full vector, right? Ultimately, our goal is to calculate the gradient, and the gradient means we are supposed to consider full vector. We should not focus on an individual entity or the single entity. Fine. So let's say it is the output of ith unit, or you can say it's the ith output, while in this case I is equals to 3, right? For our example, I is equals to 3. So what we are taking, the partial derivation of y hat I, partial derivation of the loss function with respect to y hat I. Right. And we know that what exactly the loss function is. That is minus log of y hat L. Clear? And I hope you know that the derivation, this partial derivation value, the partial derivation of minus log will be minus 1 upon y. Fine. In which case, if I is equals to L, 0 otherwise. And otherwise, it is treated as a constant. So let's say if the term is something like this, partial derivation with respect to, let's say, y1 hat, and we have minus log of y2 hat. Bookable or imaginable? Fine. So for this, what will be the answer? What will be the answer of this partial derivation? 0, right? So that is, we are exactly talking about that thing. If I is equals to L, then the answer is minus 1 upon y hat L. Otherwise, the answer is 0. Right? And in a compact form, we can write it like this. Right? We can use this notation, where the meaning of this notation is I is equals to L. Right? So instead of writing it like if and else, we are just writing it like this 1 minus 1 upon y hat L. But whenever we write this 1, it means I is equals to L. Can you recall what exactly is the name of this 1 in maths? And so that is the same thing. We have just represented it like this, whenever I is equals to L, it is 1 upon y hat L. Otherwise, it's 0. Right? So that is minus 1 upon y hat L. Clear up to this? So far we have this value. Right. Now let's think about the gradient. Right. We have taken the partial derivation with the individual entity, that is yi. Right. And whenever we are supposed to think about the gradient, what we need to do, we need to think about this. That is gradient of this y hat, and you can say the gradient of this L theta of y hat. So for that, you have to calculate this partial derivation of L theta with y hat 1, y hat 2, y hat 3 up to y hat k. And you need all that values. Agree? Fine. That actually the gradient is. We should not focus on individual neuron, but it should be of all values, right? So partial derivation of loss with respect to y hat 1, with respect to y hat 2, up to with respect to y hat k, right? And we know what exactly the value of a single or individual entity. That is minus 1 upon y hat L whenever L is equals to 1. Fine. So just can I replace this first highlighted, you can say, circle with these two circles? And now, can anyone tell me whenever we consider this particular vector, which kind of vector it is? At any instance, for any example, uh, what would be the values inside that vector? Or do we have any specific name for that vector? Can you recall any name? Identity or one hot? So for one example, if you consider one example, only one of this will be 1, one of this k will be 1, all other will be 0. Agree? Fine. So what we have done, and whenever a particular entity is 1, let's say whenever this value is 1, when this L is equals to 2. Fine. If let's say L is equals to 3, then the third element is 1, rest are 0. If L is equals to k, then last element is 1, rest are 0, and so on. Fine. So it is just an minus 1 by y hat L multiplied by with this multiplied with this one hot vector, right? So let's just represent that one hot vector as EL, right? Where EL is the k dimension vector where lth element is 1 and all other are 0. Are we fine? Right. So this you can say the gradient. Done. Have we calculated the gradient with respect to the output unit? Yes or no? Once again, the binary answer. Is this gradient that we have right now, is it the gradient with respect to the output unit? Kashyak, Jamin, yes. Answer is no. Whenever we say output unit, it consists two things, pre-activation and post-activation. So this is the result of pre or the post-activation. Post activation, right? So if you consider this diagram, now let's just focus on the diagram. It is just the gradient of this softmax, or you can say it is just the gradient of this dark green part. We haven't considered the light green part yet. Fine. So once we calculate the similar thing for the light green part, then we can say we have calculated the gradient with respect to the output unit. Is it fine? This is yet not the answer of output unit. Are you getting, everyone? Fine. But yes, this answer will help us to move forward and to calculate the gradient with respect to the pre-activation. So let's move ahead. So now let's just focus on this light green part over here, and you can also see that highlighted one. Fine. And now if I want to say this, actually this is the gradient with respect to the output, where you are supposed to calculate the partial derivation of your loss with respect to a of li, and to be specific it should be with respect to the a of l. Fine. Where I is one of the instance, right? So right now if I consider two examples, so I can be one of them, so we are interested in that. Fine. So now if I just extend this formula, we know what exactly this L of theta is. That is minus log of y hat L, right? Because it's in cross entropy, right? But you cannot directly calculate this value. So if you recall that chain rule that we have just derived before 2 or 3 slides, what we were doing, partial derivation of this loss with respect to the y hat L, and partial derivation of that y hat L with respect to a of Li, where once again this Li is one of the instance, right? But this entity, so we have to calculate these two separate partial derivation to find the gradient with respect to the output unit. Fine. Do we have any one of them? Let's say this is number 2 and this is number 1. So do we have any one of them? 1, right? So we have already computed the calculation of this first half, right? If you see the previous answer, which exactly means the first half, right? So we have that value, that is minus 1 upon y hat L multiplied with EL, where EL is the one hot vector. Fine. So now we need to just focus on the second half, partial derivation of y hat L with a of Li. But this you can only calculate if there is some dependency. If they are independent, then the answer should be 0. Right. So for that, we know that this y hat L is the softmax function, and this is the formula of y hat L. That is, this is the formula of softmax. So just look at the formula, that is e raised to this a of ALL, where this AL is actually the last layer, and this L indicates what is the meaning of this small l? Right. So that is the correct class, right? The small l means the correct class. Fine. And in the denominator we have the summation of all the I. Fine. So ultimately it depends on I, no matter whether it's correct class or it's incorrect class, but it depends due to this denominator. Agree? If we consider numerator, it may or may not depend. It depends whenever L is equals to I. But as far as we have this denominator, it will depend on any I randomly, no matter whether it's the correct class or it's incorrect class. Fine. So we can calculate that particular gradient value. Right. So now let's focus on this second part and let's try to derive the equation for the second part. Fine. So now we are calculating minus log of y hat L with respect to a of Li. And remember that once again we'll follow the same practice. Pehla I માટે કરશું and then later we'll find it for all the values of L, where if you can recall I is one of the instance. Fine. જે વસ્તુ આપણે આગળ કરી હતું સેમ વસ્તુ આપણે repeat કરશું. First we'll find for one instance and then we'll repeat with the all value, right? E value, E one hot vector આપણે એટલે જ લાવ્યા હતા. Okay. So let's start. So this value you can say this minus 1 upon y hat L, and let's move it inside where this gradient with respect to y hat L. Right. So this y hat L is actually a softmax for the L, so let's just write it as the softmax of A of L and this L, the small L, where the small L indicates the correct class. Right. Next, let's put the equation of the softmax, that is E raised to this A of LL, and in the denominator we have this A of LL. Right, and this we are supposed to calculate for all the values. And now let's see what will be the gradient of this with respect to A of Li. Right, to have a separate name, I just represented over here as I dash. Right, otherwise this I and the derivations I will get mixed up. The two may or may not be a same entity. Right, this I dash indicates the range, all different possible values, while this I indicates a specific derivative, what we are looking for. And so remember that I and I dash are not same. Right, I is a single value, while I dash is the range. Comfortable up to this point, or any doubt? Yes, no? Okay, now this partial derivation, so let's just use the formula. uh, Focus on the formula first, then we'll see the actual value. And it look bit nasty, but let's just focus on the formula first, so it might be more clear. So this is similar to, we have g of x divided by h of x, and we are supposed to calculate the partial derivation with respect to x. Right, and this is the equation for that. And I hope in the maths class you might have derived this particular equation. Right, so you can better justify this equation than me. So let's try to put the value in this particular equation. So okay, so for our case, this g of x, wherever the g of x, so this first thing is partial derivation of g of x with respect to x. Let's just focus on the g of x everywhere. Next, over here also we have the g of x. Right, so in this case, this is the g of x, right? So what we are supposed to do is, the partial derivation of g of x should be the first value. So over here we have the partial derivation of g of x is the first value. Right, also in after the minus sign in the multiplication we are using that g of x. Right, so this g of x is over here. Fine, and let me use some other color for oh sorry, this is a g of x, this is also a g of x. Once again the g of x and the partial derivation of g of x and the g of x. Now this is the denominator is our f of x, or you can say h of x. So 1 by h of x before the minus sign, before the subtraction. So this is the 1 by h of x. And after the minus sign, we have to take the partial derivation of h of x, as well as in the denominator we should have h of x square. Comfortable? And so just spend some time and just try to identify these values, right? It looks nasty, but I hope with this different color, you may able to identify that what exactly the g of x and h of x, and we have just put the values of this g of x and the h of x over here. Okay, so let's move ahead. Let me just go back and let me just erase this all values now. So this is the equation that we have now, and let's see further modification or further simplification. So now if you consider the first half, just focus on this highlighted half only, right? The remaining things are as it is. We haven't changed anything else. Fine. So let's just focus on this first box and let's see how we have reached towards this value from the first box. So that is the partial derivation of e raised to x. If you see the equation, that is the partial derivation of e raised to x. Right. So we know that the partial derivation of e raised to x is equals to e raised to x itself. But this is true whenever this L and I both are equal. And otherwise, we have some value over here in the partial derivation. Let's say I is equals to 1 and L is equals to 2. Fine. So in that case, the answer is 0. Right. And it is treated as a constant. So this is true, that is partial derivation of e raised to x is equals to e raised to x whenever L is equals to I, right? So, and to represent that L is equals to I, we have used this notation, right? So in previous slide also we have used this particular notation. Fine. So that means 1 multiplied by e raised to x if I is equals to L, otherwise 0 multiplied by e raised to x, that means nothing, right? 0 if I is not equals to L, right? So that is if else, and to represent that if else we have just written this particular one. Fine. Next, this second part. So now we have the summation of e raised to x. So once again, this value is e raised to x when whenever I is equals to I dash. Right. So if you observed, the partial derivation is with respect to I, that is a of Li. Right. And this I dash, as we have mentioned previously also, this I dash is a range, right, which include the I also. Right? So whenever I dash is equals to I, at that time this is just the e raised to x, otherwise it's 0. Fine. So now what we have replaced, we have just considered I over here, right? So which itself means that whenever I dash is equals to I, this is the answer, right? And otherwise you can also represent it like this, right? You can write like this 1 whenever I is equals to I dash. Right? Both are the same thing. So just focus on this part, how we have derived these two part, and I hope it's clear now. Fine. Now let's just see the denominator. So this denominator as it is. Now over here we have a square of denominator. So we have just divided that square into two part, where the first part we are applying with this e of x, and another with this latest calculation that we have just done. Fine. Now just look at this equation. Have you seen this equation anywhere? Exactly, it's a softmax, right? Similarly, what about this? And also think about this third part. Fine. So the first part, second and the third all are the softmax, but the point is this is a softmax for, you can say, L, right? This is for I, and this one is for L whenever I is equals to L. Fine. Let's plot the value of the softmax now. So this is y hat L. This is once again y hat L, and this is y hat I. Fine. And now if you further simplify, this y hat L is common, and which will be nullified with this particular y hat L, and now we're just left with this equation. Fine. So this is the final output for the partial derivation of the output unit. Agree? Or output layer, agree or not? Answer is no, because this is the final output of partial derivation with respect to one entity of output unit. Now once again we need to repeat the same exercise that we have done with the after activation layer. Do you have any lecture after this current lecture? Okay, so break. So let's just conclude this, right? It may take less than 5 minutes. So we have this simply now what you need to do, you have this value for a single ith element, right? We have just derived this value for ith element. Now we need the gradient, which is with respect to all the elements. So that is A of L, right? So that means you need to have partial derivation of loss with respect to A of L1, with respect to A of L2, with respect to A of L3, up to with respect to A of Lk, right? This is just with respect to A of Li. So simply similar to the previous calculation, the values are like this. Whenever L is equals to 1, it should be 1 minus, you can say, y hat 1. L is equals to 2, it should be 1 minus y hat 2, and so on. Fine. And we know that this term will refer as E of L. So this is the final answer. Minus E of L minus y hat. Right? Where this E of L and the y hat are scalar or vector? Vectors. Fine. Excellent. So that's it for today, and we have completed the partial derivation, you can say the back propagation with respect to easiest unit, that is the output unit, right? Because in the beginning itself we have seen that it is for the easiest unit, that is the output unit. Now we are supposed to calculate the same thing with respect to the hidden as well as the other unit, and so that will continue in the next session or the next lecture.